Hello everyone, welcome to GPU Teaching Kit Module 14. We are at lecture 14.3, Overlapping Data Transfer with Computation. The objective of this lecture is for students to learn how to overlap data transfer with computation. In particular, we're going to teach them how to write CUDA host code to achieve asynchronous data transfer. And also, we're going to go over some of the practical limitations in older CUDA hardware and how the newer hardware address these limitations. This slide illustrates the use of stream in CUDA host code with our vector addition example. Before we can use these streams, we need to create them. In CUDA, we have a special data type called CUDA stream underscore T. These are the data types that can be used to declare handle variables for these streams. And these handle variables actually get allow the program to access the queues that implement these streams. So at the beginning of the code, we showed that we created two stream handle variables, stream 0 and stream 1. Once we declare these variables, we can call CUDA stream create with the address or pointer to these variables so that the function, the CUDA stream create function, will allocate memory, initialize the data structure, and have these string handles to point to the corresponding data structure for the streams. The second part of the code declares the chunks of device memory that will be used to transfer the data in a chunked manner, as we illustrated in the previous lecture. Once we declare these chunks of device memory, we can use CUDA malloc to allocate these memories in the device memory, just like what we had in the past. Now that we have set up the use of streams, we can write a for loop in the host code, and the for loop will iteratively take chunks of A and B and transfer them into the device memory, and launch kernel, and eventually copy a chunk of C back into the host. So we start at the beginning of A and B, and then each iteration will take care of two chunks of A and B. So that's why I is incremented by segment size times 2, because each iteration would take care of two chunks of A and B and generate two chunks of C. Inside the loop body, we show that we would call CUDA main copy async, and we're going to use stream 0 for A and B. And then we will call the kernel launch, and we will also use stream 0 to process A0 and B0. And after the kernel launch, we also call the CUDA main copy async, and then we would to stream 0. So these four statements will enter the CUDA main copy for A, for B, and the kernel launch and the CUDA main copy for C, all into the same queue for stream 0. The next batch of code will enter the copy of A1, B1, the kernel launch for B1, and then copy back C1 into the queue for stream 1. So after the iteration, we should have four statements or four tasks in the stream 0 queue and four tasks in stream 1 queue. We will iterate the process. So in each iteration, we will enter four tasks into stream 0 and four tasks into stream 1. As we mentioned in the previous lecture, we expect all the tasks for stream 0 to enter the stream 0 queue, and all the tasks that correspond to stream 1 to enter the stream 1 queue. Unfortunately, in some of the earlier GPUs, there was not physical queues in front of the copy engine. So what happens is that the queue actually gets implemented as real physical queues in front of the copy engine and the kernel engine. So we see that there is a queue in the copy engine and there's a queue in front of the kernel engine. And the streams 0 and 1 are entered, tasks are entered into these queues. So the stream 0 memcopy and stream 1 memcopy are actually entered into the same physical queue in front of the copy engine. So now we see that in the code sequence that we had in the previous slide, the main copy for A0, B0, and C0 will be entered into the queue before the main copies for A1, B1, and C1. Same thing with the kernel launch 0 and 1. And this physical queue implementation that mix the streams of 0 and 1 actually will have some real implication in terms of the degree of overlap we can achieve with the code that we showed in the previous slide. In particular, when we look at the next timing slide, I want you to remember that the main copy Z0 is in front of the main copy A1 in the physical queue. As a result, when we look at the timing diagram in this slide, we will have the memory transfer for A0 and B0 released from the queue, and then the compute of C0 will be underway. And then eventually we would release the transfer of C0 into the copy engine. Unfortunately, because C0 is in front of A1, A1 and B1 will not be released until C0 is released. That's why we're showing the beginning of execution for A1 to be slightly after the beginning of execution for C0. What we wanted was to have A1 and B1 transferred when C0 is being computed. So this timing shows that we failed to achieve what we wanted to achieve in terms of the overlap between data copy and the compute, but using the code that we showed in the previous slide. With that in mind, the CUDA programmers who wanted to achieve memory overlap between data copy and computation use the code that we're showing in this slide. So within the for loop, we actually mix the code from stream 0 and stream 1. Immediately after we have the CUDA main copy async statements for A0 and B0, which correspond to stream 0 and stream 1, we immediately have the CUDA main copy async for A1 and B1, and they correspond to stream 1. And these two batches of memory copy are then followed by the vector add kernel launch. One correspond to the generation of C0 in stream 0, and then the other one correspond to the generation of C1 in stream 1. And finally, we have the two memory copies for C0 and C1 back to the CPU, and each one correspond to stream 0 and stream 1. And so the code is less natural, and it mixes the code sequence for the mem copy for the two streams, and this is what we call the interleaved code. So when we execute the code in the previous slide, we will see that the main copy A0, B0, and main copy A1, B1 will enter the copy engine before the main copy C0 and C1. Of course, the driver will also maintain the dependency between the main copy and the kernel. So we're showing that the kernel 0 will be looking at main copy A0 and B0, and it will not be released into the copy engine until main copy A0 and B0 have been performed by the copy engine. And so this is shown as the two arrows from kernel 0 to the main copy of A0 and B0. And this is to enforce the dependency or the sequential execution requirement of the tasks in the same stream. Now with this order in the copy engine queue, now have the following timing diagram. We see that A1 and B1 can now go into the copy engine while the kernel for calculating C0 in stream 0 is underway. So this achieves the overlap that we wanted to achieve in the original design. Unfortunately, we don't have a complete ideal overlap execution timing for the next iteration. When we go to the next iteration of the for loop, we actually wanted to transfer B2 and A2 and B2 while the calculation of C1 is underway. And in fact, A2 and B2 will be using the variable A0 and A0 and B0 in the host, in the device memory. Unfortunately, because A2, the transfer of those two A and B chunks are entered behind the memory transfer for C1 in the copy engine, they will be trapped behind C1 and they cannot be released until C1 is released into execution. So this fails our design to overlap the transfer of A2 and B2 with the compute of AC1. In order to achieve the ideal timing, we actually need to have at least 3 buffers for each of the original A, B, and C chunks. So we need to declare 3 chunk variables, A0, A1, and A2, B0, B1, B2, and so on. And so the timing diagram that we're going to use to try to achieve is that we need to be to mix A2 and B2 with the compute. So we actually need to have more than 2 chunks in each iteration, and we will leave the code as an exercise for the students. It is precisely because of the complexity involved in achieving the ideal overlap timing diagram in the older GPUs. The newer GPUs are now designed to alleviate those kind of problems. So instead of having just one queue in front of the copy engine and the kernel engine, now the newer GPUs have the hyper queues, and essentially these are there are multiple queues in front of each engine, and these queues truly give the stream 0, stream 1, and stream 2 their own individual queues, so that any operation in stream 1 will not be stuck behind an operation in stream 0, and so on. So this allows a much more concurrency by allowing some streams to make progress for an engine where others are blocked. And this avoids the blockage of some operations from one stream by other operations in another stream. I mentioned briefly that there's support for synchronizing with CUDA stream tasks. So here we show two synchronization commands that will help the host code to synchronize with the activities in CUDA streams. The first one is CUDA stream synchronize. And this function takes one parameter, which is the stream handle variable. And it's used in the host code. And the function, once executed, will force the host code to wait until all the tasks in the stream identified by the stream ID to have all completed their execution. For example, if we execute CUDA stream synchronize stream 0 in the host code, it will ensure that all the tasks in the queue of stream 0 have completed before the host code can continue execution. This is different from another synchronization statement called CUDA device synchronize. This is a synchronization function that allows the host code to wait until all the tasks in all the streams have completed for the current device before the host code can proceed or continue with its execution. Because it's going to be waiting for all the tasks in all the streams, it does not require any parameter. These two synchronization functions are frequently used in CUDA host code to make sure that the CUDA host code wait until either all the tasks in a stream have completed or all the tasks in all streams have completed before executing the next the next host statements. This concludes lecture 14.3 of the GPU teaching kit. Thank you.